Hey everyone, how goes it? Welcome back to Computer Science 146. Today, we're going to continue discussing heaps. In previous lectures, we've discussed the tree data structure. And this is a data structure that can be defined recursively as a collection of nodes, where each node is a data structure consisting of a value together with a list of references, or edges, to other nodes, with the constraints that no reference is duplicated and none points to the root. So in other words, trees have nodes and edges, and trees cannot have a cycle. In a previous lecture, we also introduced the heap data structure. Now this is a binary tree structure. Once again, the node's data must be comparable in some way. As it's a binary tree, each node has at most two children, a left and a right child. Now we also demonstrated how a heap could be implemented inside of an array. Now in these examples, we're assuming that the root is at index 0. In order to calculate the left child's index, you simply take the parent's index, multiply that by 2, and add 1. In order to calculate the right child's index, you take the parent's index, multiply it by 2, and then add 2. And in order to access the parent's index, you take a child's index, subtract 1, and then divide that by 2. So if we were at index 1, right here, and we needed to get the left child, if we do 2 times 1, which is 2, plus 1, that's index 3, that's the left child. Likewise, if we multiply this times 2 plus 2, we get the right child. Now, if we were right here at the right child and we needed to access the parent's index, what we do is subtract 1 from 4, which is 3, and then 3 divided by 2 is 1. The reason why this is correct is, remember, indices have to be integers, and in integer division, 3 divided by 2 is 1 because it chops off everything past the decimal point. Integers are only whole number values. Now that we understand this, let's go ahead and start implementing a min heap. Now this opening part is going to be very similar to how we implemented the max heap. So first we're going to create a new class, just call it min heap. Now one of the properties of a heap is each of the node's value must be comparable in some way. If we make this an abstract data type by putting in the generic type t, in order to ensure that the values are comparable, we take t and make it extend type comparable of type t. Now we're going to do the array implementation of a heap again, so I'm going to create a private t array, call it the heap, and then I'm going to set up a constant value that corresponds to the default size. Public static final int default size, and I'm just going to set it to 128. Now I'm also going to create a private int last index, and this is going to keep track of the first null element. Now we're just going to create some constructors. Public min heap, here's our default constructor. Then we'll create another public min heap, and our parameterized constructor is going to take in an int size. Then I'm going to create a private void initialization init, giving an int size. Now, if the size that we passed in via parameter happens to be greater than 0, we consider that a valid size. Then what we need to do is construct the heap as simply a t array of a new comparable array of this size. And also set the last index to 0. As this heap starts out empty, we correspond the root index as being 0, so that way we just say the first null element is the root. Now, if the size happened to be incorrect, so it was less than or equal to 0, we still want to ensure that the heap has been created in some way, so we're just going to recall init and pass in this default size. From the default constructor, I'm just going to call init with the default size. And from the parameterized constructor, I'm going to pass the size parameter into the initialization in order to construct this heap. Now that we've created the heap, let's take a look at some of the functions of a heap. So as it was described before, add works in a very similar way with the min heap. First, what we need to do is replace the first leaf in breadth order with the new data. From there, we need to bubble up the data if it is necessary. Now, the bubble up process is if the child's data, in this case, is smaller than the parent. Then we swap the information. We continue swapping the child's data with the parent data until the parent is smaller than the child, or we reach the root index. For example, if we're going to add the value 0, then first what we do is we scan through and find the first null element in breadth order, and it's right here. We insert it there, and then we start bubbling up. We look at the parent's value. 6 minus 1 is 5 divided by 2 is 2. So then we look, is 0 less than 2? It sure is, so we need to swap that value. Then we have to continue this process. Then we need to look at the parent from here. 2 minus 1 is 1 divided by 2 is 0. Is 0 less than 1? It sure is, so we need to swap it. And now because we're at the root, we can stop. Now let's implement add for this min heap. Now this is going to look very similar. Public void add t a data. Going to add some data into this heap. Now if the last index happens to be greater than or equal to the heap.length. Now as this is an array implementation, we might run out of room. So in this case, we simply need to return because we don't have an empty space left in our heap. Now if that's not true, we assign heap at the last index. Now remember, the last index is the first null element. The way that we're keeping track of this will be the first null element in breadth order. We just assign this to the data. Then we'll do to do bubble up, and then from there, the last index plus plus. Now we're going to create private void bubble up. And we need to start this bubble up procedure. Also, so we don't forget, I'm going to go ahead and replace this to do with a call to bubble up. Now for here, we need to keep track of an index. And we need to start at the last index, what it currently is. Because notice, we call bubble up before we increase it. So this means we have already added the data at this last index, and then starting from this last index, we start that bubble up procedure. Now while this index is greater than 0, so we're not at the root, and now we need to examine what the parent's data is. So we're going to do heap at the parent's index. And the way that we access the parent's index from this given index is simply the index minus 1, then divided by 2. As the data has been ensured to be comparable, we can call compare to what is that heap at this current index. Now, if the parent happens to be greater than the child, this is out of order, so we must swap. So we take ttemp is equal to, let's start with the parent. So the index minus 1 divided by 2. Then we reassign the parent, index minus 1 divided by 2, with our current index's value, heap at this index. Then we reassign heap at this index is equal to that temporary value, and then we must update where this index is by going up to the parent. So simple enough, index is equal to the index minus 1 divided by 2. And this is the add procedure for a min heap. Just notice, basically all that we needed to change was this sign. For a minimum heap, the value of the parent has to be less than the value of all of its children. Next, let's take a look at remove. The remove procedure works in a very similar way. What we first do is store the data that is found at the root. Now for a heap, you can only remove at the root. After we've stored that information, we then replace the root data with the data in the last node in breadth order. From there, starting from the root, we start bubbling down that information. Once we've bubbled down, we return the stored value previously at the root. Now to go into more detail, when you bubble down, what you do in this case is you pick the smaller of the two children, the left or the right. If the value is smaller than the parent, then you swap those values. And then we continue this until the parent's value is smaller or we reach the bound of the tree. So let's say that we call remove. Well, the value currently at the root is 1, so we need to store that value. From there, we need to find the node, the last node in breadth order, which is this one right here. Then we need to remove this value and add it up here, just like that. Now that we've done that, we need to start bubbling down by looking at the two children, the left and the right. Which one is the smaller child? The right one. Now, is the parent greater than the child? It is. So we need to swap. And now we're done because we're at the bounds of the tree. And once we finish that, we return that value. Let's remove one more time just so we can see this. So first we store the value at the root because that's what we're going to return. Then we look for the last element in breadth order, and that's right there. We remove that and then replace the root's value with that value, just like this. Now we start bubbling down. We look at the children left and right starting from the root. Which one is the smaller child? Well, 3 is smaller than 4, so we look at that one. Now, is 6 greater than 3? Yes, so we swap. Now we continue this procedure. We look at the left and the right child. Well, the thing is, there is no right child, only the left one. Now we have to look. Is 6 greater than 5? Yes, it is. So we have to swap it. And now we're at the bounds of the tree, so we're done. Once we're done bubbling down, we return the value, and we're finished. Let's see an implementation of remove. Inside of our code, we're going to create public t remove. We always remove from the root. Now, one thing to keep in mind is the tree might be empty from the beginning. So we can check that by if the last index happens to be 0, then we have an empty tree, so we must return null. There's nothing in there, so we need to return nothing. But otherwise, we need to store this return value is what is found at the root, in other words, index 0. Now we replace the value at the root, heap at index 0, is equal to heap at the last index minus 1. Now remember, the last index was the first null element in breadth order. If we basically subtract 1 from that, that is the last value in breadth order. From there, we want to make sure that this value that's just replaced the root doesn't exist anymore. So we take heap at the last index minus 1 and just assign that to null, so we lose the reference. Then last index minus minus, to do bubble down, and then return ret. Now we need to write the bubble down procedure. Private void bubble down. Now to make sure that we call it, let's just call bubble down from right here, and we're good. Now the bubble down procedure starts at the root. So let's store a reference int index is equal to 0. Now we need to keep doing this until we reach the bounds of the tree. So while the index, now let's just assume we're looking at the left child, times 2 plus 1. while that is less than the last index, that means we're still at least within the bounds of the tree. The last index is the first null element, and as long as this value is less than that value, then we should be good. Now let's make the assumption. Let's say that the int small index was the left child, index times 2 plus 1. Now we need to confirm that assumption by first checking if index times 2 plus 2, the right child, is within the bounds of the tree, last index. So while that exists, now we need to check the value of the left and the right child, because maybe our assumption was wrong. The left child was not the smaller of the two, and it was actually the right child. So and heap at this index times 2 plus 1, the left child, if we compare that to heap at the index times 2 plus 2, and compare to returns a value that is greater than 0, this means that the left child was greater than the right child. And in this case, we reassign the small index to the right child, index times 2 plus 2. Now we still need to compare whichever was smaller with this current index. So if heap at this current index dot compare to heap at the small index, whether it was the left or the right child, if this happens to be greater than 0, then we need to swap those values. So ttemp is equal to heap at this index. Heap at this index is equal to the heap at the small index. So it could either be the left or the right child, but either way, we just stored that reference into the small index. Then finally, heap at the small index is equal to temp. Now, if we compare this, and this was not true, we need to break. Because that means the parent was smaller than the smallest child, we don't need to check anymore. Yet, if we don't break, we need to reassign index to the small index and keep bubbling down this tree. So this is the remove procedure for a minimum heap. And basically all that changed was checking, is the parent greater than the child, and if that's the case, you swap. Now another method that we're going to write, we're just going to print out all the values in breadth order for a heap. That could be done very simply. Public void print. Now because this is a tree but is implemented as an array, we can simply just use a for each loop in order to print out all the values. For each t, h in heap, so inside of here, if h is equal to null, because we might have null elements we need to break, but otherwise, system.out.println h. Easy enough. Now that's everything that we implemented the last time, but now I want to introduce a brand new sorting algorithm that uses a heap. Okay, so here we go. This is how you do heap sort. You add all values to the heap, then you remove all the values from the heap, and you're done. Wait, what? No, really, it is that straightforward. It turns out a heap is a priority queue, and as you add values to the heap, it maintains whatever the heap property is. For a min heap, all the values are smaller than any of the children. Now, when you remove all the elements from the heap, it removes them in sorted order. Let's see exactly how this works. Let's say we had the values 5, 1, 4, 3, 6, and 2. Well, let's add them one at a time. So first, we add 5, there's the root. Now we add 1 in breadth order, which is added to right there. Now we bubble up. 1 is less than 5, so we swap the values. Now we add the value 4 in breadth order, so it's there. Now 1 is less than 4, so it stays there. Then we add the value 3 in breadth order. Now 3 is less than 5, so we swap that. 3 is not less than 1, so it stays there. Then we add the value 6. Well, 3 is less than 6, so it stays right there. Then we add the value 2, which is added right there. 2 is less than 4, so we swap. Now that we've added all the values, let's remove all the values. Now the first value that we remove is 1. Notice 4 replaced 1, then we need to bubble down. The smaller of the two children was 2, so we swap those values. Next, we remove again. So the value returned is 2, and that is replaced by 6. Now the smaller of the two children is 3. 3 is less than 6, so we swap. 5 is less than 6, so we swap. Then we remove again. The return value is 3, so 6 goes back to there. The smaller of the two children was 4, so we swap. Then we remove again, return the value of 4. 6 goes right there. 5 is less than 6, so we swap. Return that value. Now we only have one value left. Return it, and we're done. And notice that the returned values are 1, 2, 3, 4, 5, and 6. Now, let's see how we can implement heap sort given the code that we've written. So I'm going to do this in kind of a unique way. I'm going to create public void heap sort with a T array of information. So someone can pass in this comparable type T array inside of this, and it will sort it. First thing we need to check is if the array is equal to null. We need to simply return because there's no information inside of this. Now, if that's not true, I'm going to create an instance of this min heap of type T, call it mHeap, and construct that as a new min heap of type T with the array.length. So wait a second, we created an instance inside of this instance? Well, yes, we're assuming that this array has not been sorted, but it is at least comparable, so we're going to create an instance of a minimum heap inside this minimum heap, and then utilize its properties in order to add each one of the elements from this array to this min heap, and then remove each one of the elements from that array to the min heap. Now from here, here's what we do. So then what we're going to do is for int I is equal to 0, I is less than this array dot length I++. We're going to take this mHeap and we're simply going to add the array at index I, each element inside of this. Then what we're going to do is replace all of the elements in this array with those values. Watch. For int I is equal to 0, I is less than array.length I++. We're going to assign array at index I and replace that with mHeap.remove. Now let's see an instance how this works. I'm going to go ahead and create a tester class with the main method. Now that we have this tester, let's go ahead and create an instance of this min heap. So let's make a min heap of type integer and just call it iHeap is equal to new min heap of type integer and call the default constructor. Now notice, I can't just use lowercase int for integer because the thing is, the type T is assumed to be a comparable type, and that comparable type is a class type. In order to do integers or doubles, what we need to do is use the wrapper class in order to make it a class type of those primitive types. Now similarly, I need to create an integer array. I'll call it iArray, and I'm just going to assign the values that were found inside of our example. 5, 1, 4, 3, 6, and 2. And now I can call iHeap.heapSort this iArray. From there, I'm going to do for each integer I in our iArray, system.out.println, the value at I, and let's see if this worked. And sure enough, 1, 2, 3, 4, 5, 6. By using the properties of a heap, we can easily implement this sorting algorithm. However, we now have to consider what is the complexity of this sorting algorithm. Well, once again, we can assume that the worst case was everything was sorted in descending order. The operations of heap sort is we have to add all n values to the heap, followed by removing all n values from the heap. Now, the way that a heap is set up, a heap is always going to be a balanced tree. Now, this is unlike a binary search tree, which could be unbalanced. So, as we know, a balanced tree, starting from the root to any of the leaf values, is log n. This means we have to add n elements, which will take log n cases, then remove all n elements, which will take log n complexity, or for short, heap sort is n log n complexity. In the past lectures, we've continued to explore the heap data structure, and in this lecture, we introduced how the heap can be used to sort information. And with all that being said, I'll see you next time.